Shoulda, coulda, woulda, but it's too late. Shouldn't catch feelings on the first date. Oh, oh, 0 to 100, no first base. Ended up with coffee back at your place.
Self-driving cars have been all over the news in 2017, with companies like Tesla and Uber making headlines developing the technology in one way or another. My name is Rahul, and in this video I'll show you how to get started making your own self-driving cars so that one day you can make headlines too. All you will need to follow this tutorial is to clone my Git repo and then download the Udacity Self-Driving Car Simulator, both of which are linked in the description. You don't even need an actual car to get started, so let's get to it. The neural network we will use to train our self-driving car is the tried and true CNN. You can think of a CNN as a detective taking a magnifying glass and scrutinizing an image for important details. These important details are known as features, and are what a CNN uses to identify objects in an image rather than using the whole image in its entirety like a basic deep neural network would. This is important for a self-driving car, since the car should be able to distinguish the road from its details rather than from remembering what a road looks like from every angle. The model we will be using is based off of this paper on self-driving cars by NVIDIA. Their model uses 3 RGB images from left, right, and center cameras and feeds them through a series of CNNs to extract features from the image. Those extracted features are then fed through some fully connected layers like a typical deep neural network. The weights are tuned by the Atom Optimizer in order to minimize the difference between the neural network calculated output speed and angle and the speed and angle recorded in the data. Training a self-driving car off of human recorded data makes a lot of sense rather than giving a car a series of rules and constraints to algorithmically follow. If you think about it, observation and practice, rather than following a set of rules, is really how even humans learn how to drive. In the case of our self-driving car, we're going to collect data in pretty much the same way. Open the Udacity driving simulator and go into training mode. Then whenever you're ready, hit the record key and start driving. I typically found that I only needed to make one lap around the test track in order to get a working model, so I would recommend driving 1 or 2 laps. For ideal results, it helps to use a joystick or a controller so that the turns aren't as sharp or inconsistent in the data, but I just went ahead and used the keyboard for this example. When you're happy with the data you've collected, you're now ready to go through the training process. Make sure you cd to your clone project folder and activate the conda environment by the appropriate command shown on the screen. The command to trigger the training is also on the screen above. Feel free to pause the video if you need more time. The training took about half a day on my 15-inch MacBook Pro CPU, so once you've got it started, let's go ahead and take a look at the training code in greater detail to understand what's going on. I've broken up the training code into 3 parts, which are the data processing stage, model graph creation stage, and running the training. The data processing stage has some noticeable differences from the NVIDIA model. For one, we will not be using the left, right, and center training images at the same time. As much as I'd like to use all 3 images at the same time, or train 3 separate models for each camera, the cost would either be in time or in better hardware, since convolution operations are so expensive. To make up for a decrease in accuracy, I instead just added each left, right, and center image as its own image to the training dataset, and adjusted the input angle for the left and right images so that all images would essentially be center images. This way, there would be a greater diversity of images used for training as well as the quantity, since each image fed to a CNN acts as a vote for which features should be kept as important. Using a diverse but relevant set of images greatly helps us improve the model performance. Next, I doubled the training dataset by duplicating the recorded dataset and adding additional image processing to the duplicated images. This includes adding fake shadows, randomly changing the brightness, shifting the photo, and flipping the images. This allows our model to be trained for different scenarios that we haven't collected the data in. Finally, I cropped all the images to remove irrelevant parts of the image data, such as the sky and the landscape that our car shouldn't be making driving decisions on. Now let's move on to the model code. I modularized the TF computational graph building function calls into a few functions to make the code as easy to understand as possible. I started off by normalizing the data, which makes it much easier for the optimizer to do its job by keeping all the input points in the range -1 to 1. Then the model is ready to begin the convolution and pooling operations. The convolution steps use same padding and use strides of 1. Using strides of 1 is important since anything greater than 1 would cut out crucial image data. When driving a car, we really don't want to be ignoring parts of the road. I experimented with using valid padding, but this caused the car to have a slightly harder time staying on the road as it began to drift off. I realized this made sense, since valid padding doesn't give the edged parts of the image the same spotlight that same padding does. Anyways, since I already cropped out the irrelevant scenery data, I thought it made sense for the model to scrutinize every part of the remaining data as thoroughly as possible. Another thing to note is that the convolution steps start off with a kernel size of 5x5, but then go down to 3x3 to adjust for the fact that the feature map dimensions become smaller from the pooling. I use max pooling instead of average pooling, since max pooling does a better job of retaining only the defining features compared to average pooling, given how noisy the images are. When I experimented with average pooling, the extracted features were most likely just turning into mush, and the car had a harder time staying on the road. After the convolution and pooling steps, there is a dropout step before going into the fully connected layers. I thought this was somewhat out of place at first, since I would have expected dropout to better serve its purpose between the fully connected layers instead. I reasoned that NVIDIA designed their model this way to prevent the extracted feature data from passing through the layers inconsistently due to dropout, and confuse the model. By having dropout occur beforehand, overfitting could be reduced and the training could remain more consistent. I included a final named operation that doesn't affect the output data, so that when our model is used by our self-driving car client code, it can access the output vector. The final thing to point out is that the extracted feature maps were reshaped into vector inputs for the fully connected layers, the same as is done when training MNIST data. Now that the computational graph has been built, let's go through the training code I've written. TensorFlow placeholders are used for the input training data and labels. The output steering angle comes from the model scheme function we just went over. The cost function is defined by taking a difference of the output steering angle and the recorded steering angle, which is then squared, and is what we want to minimize at each training step by using the atom optimizer to tune the weights. The atom optimizer is pretty much the standard optimizer used, and the cost function used is nothing new either. Keep in mind, we are not doing classification, so there is no cross entropy or softmax used here. At each step of the training, a random batch from the training data is chosen to perform stochastic gradient descent. Remember that stochastic gradient descent is much faster than using standard gradient descent, and that we make up for the lack of accuracy due to using the small batches of the training data by increasing the number of steps. For every 100 steps, I'll calculate and output the cost for debugging the hyperparameters. Keep in mind that the dropout rate is 0 here, with key probability set to 1, since we are doing a calculation and not training. After an epoch is passed, which is also user specified, the program then goes ahead and saves the model.
Once you have your model trained, you can go ahead and open up autonomous mode on the self-driving car simulator and go to your project folder and enter python drive_tf.py and choose a meta file, which will basically be your model file, and try to choose the latest one. Remove .meta at the end and hit enter. Keep in mind you're going to have your conda environment activated for this to work, so make sure you do that first. Now wait for a while for it to fire up, and once it does, you can see it's computing this angle, throttle, and speed at the right side and setting it to this simulator over here. Now it is a bit laggy. I do have a lot of computational tasks going on in the background right now, so as you can see it's pretty delayed and it's resulting in this drunk driving. But for the most part it is staying on the road, and let's just see if it's going to make this turn here. Fingers crossed that it does. And moment of truth. Alright, cool. It seemed to manage to do better on the turn. But yeah, I mean, for the most part, like I said, it really matters how well you drive and the data you collect as well. And for you, it might be better results. I'll go ahead and record footage of this through my cell phone camera so I don't have the lag. But for the most part, you can see it's working here. So anyways, that's pretty much it. Hope you learned something. Leave a like and a comment below, and if you want to see more videos like this in the future, then yeah, just be sure to subscribe. Anyways, that's it for me. That's Rahul signing off.